Good afternoon, everybody. I'm very happy to chair this session. I'm Kiyoshi Ueda from Japan, and we are going to have 5 excellent talks in the field of photon impact. And the first speaker is Patrick O'Keefe from Siena, Italy, and he's going to talk about 2-color photonization of atoms using extreme ultraviolet and optical laser radiations. Let's see what we can learn from such kind of experiment. Patrick?
Good afternoon, everybody. I'd like to start by thanking, of course, the organizers and the scientific committee for giving me the chance to present these results at this very interesting conference here in Toledo. So I'm going to talk about 2-color photoionization using XUV pulses together with optical laser radiation. And the 2 types of XUV sources which I'm going to talk about are free electron lasers and synchrotron experiments. So basically, I'm going to start off the talk with a comparison between these 2 kinds of experiments and the kind of experimental techniques which we use at the 2 facilities. Then I'm going to go on and give 3 examples of laser plus synchrotron experiments of increasing complexity, passing from helium to neon to xenon. And I'll finish off in the last part of my talk with a description of some helium nanodroplet relaxation dynamics investigated using the free electron laser Fermi in Italy. Okay, so just to go in softly into the talk, the synchrotron radiation, 3rd generation, have the characteristics of having about 10 to the 12 photons per second, which may sound like a lot, and indeed it is for most experiments, but one has to take into account the fact that the repetition rate of a typical synchrotron is on the order of hundreds of megahertz. So this means that in every single pulse, there's only a couple of thousand photons. And this means that if you need to do 2-photon experiments, the cross-sections of the XUV step need to be extremely high to be able to do these kind of experiments. And indeed, if you look at the literature, you'll find that about 99% of laser plus synchrotron experiments are done on atoms, where the cross-sections are tens to hundreds of megabarns. On the other hand, at the free electron laser, we've got up to 10 to the 14 photons per pulse, and this means that we've got 10 to the 14 photons arriving in the space of 100 femtoseconds. And this clearly means that we have a relaxation on the requirement for high cross-sections. Indeed, as we've heard in a number of talks during this conference, it leads to a lot of nonlinear processes where you can have multiple photons absorbed. Although in the case of the experiments I'm going to talk about, we've reduced the intensity of the felt to be able to avoid these kind of nonlinear processes. And obviously, the other advantage is that we can get down to dynamics on the time scale of hundreds of femtoseconds. Okay, just to go in quickly into the experimental technique, this is a cartoon of how the velocity map imaging works, which we've used for these experiments. So we've got a beam of atoms coming in from the top. We send in and focus our synchrotron radiation on the atomic beam to excite excited states, and ionize that with the laser propagating from the other side. At this point, we form a cloud of electrons which expand on their way to the detector as they're pushed by electrostatic lenses. And at the end of the time of flight, the 3D ensemble is projected onto the 2D position-sensitive detector. And this allows us to be able to extract out from that, we can go on through. To extract out from this 2D projection, we can invert the image, get a slice through the original 3D distribution, and extract out the photoelectron and the angular distribution. Now, this is a very well-established technique, and it's been around since the late 90s, essentially. Okay, so what are the variants on this kind of technique, which we use at the synchrotron and at the free electron laser? Well, at the synchrotron, we use coincidence spectroscopy. So we not not only do we do electron velocity map imaging, but we also record the ion formed in coincidence, which is sent in the opposite direction by the electrostatic optics. And this means that we can, in addition to allowing us to get a better signal to noise, we can also identify the electron, or the ion with which the electron was formed. On the other hand, at the low-density matter beamline at the free electron laser, where the repetition rate is about 10 hertz, we can no longer do that trick because we have a lot of electrons being produced at the same time, so we can no longer univocally match the electron to the ion formed at the same time. Okay, so moving on to the question is, why do we want to do two-photon experiments? Well, in a one-photon experiment, the angular distribution of the electrons formed is given by the traditional angular distribution formula, in which there's only one experimental parameter, the well-known anisotropy parameter. On the other hand, in two-photon spectroscopy, we actually get a more complicated photoelectron angular distribution due to the possible interference between outgoing channels. And we get an extra angular distribution parameter in the experimental data, which gives us extra information on the photoionization process. Well, this may not sound like much, but in reality, if we take the first example from the synchrotron work which we did at gas phase, for example, if we ionize helium with the synchrotron radiation with one photon, we ionize an s orbital of the helium into the p continuum and obviously we get an angular distribution with a beta parameter of 2. Now, if on the other hand, we use the synchrotron radiation to pick out a transition where we excite an s electron into a 3p orbital, what we do is we essentially align the total electronic angular momentum of the intermediate state along the electric field vector of the exciting light. And then when we ionize that aligned intermediate state into the continuum, we get a much more peaked angular distribution, from which we can then extract out the two beta parameters. And the good news about this is that we can relate these directly to the parameters which describe the photoionization process, and that is the ratio between the integrals of the radial matrix elements describing emission of S and D waves and the phase difference between these two. So essentially, from a single experiment, we can get a complete description of the photoionization dynamics. So we went a little bit further with this experiment in that we went up higher into the Rydberg series, going to Rydberg levels n equals to 4, 5, and 6. And this experiment gets more and more difficult as you go higher into the Rydberg manifold because the cross-section drops off with 1 over n to the cube. But for example, for exciting through the 5p state, these are velocity map images corresponding to ionization at different energies in the continuum. You can see that we have sufficient signal to be able to do this experiment. So extracting out, for example, the red points here extracted directly from these images are this is the phase difference as a function of the electron energy in the continuum, where the blue points come from a previous experiment by Steve Leone's group using high harmonic generation. You can see that the agreement is pretty good. On the other hand, this is the ratio between the outgoing S and D waves. You can see that the ratio actually depends on the intermediate state, and these are calculations by Andrei Mikhailich. You can see that they depend ever so slightly on the intermediate state, and unfortunately, the experimental points have quite large error bars. So although we can say that the calculations are not wrong, we can't confirm that there are a very small variation of the intermediate state. Okay, so that was the simplest example. So the next step on the ladder is obviously neon. And in this case, we've got spin-orbit split ion threshold. So we've got the 3/2 threshold, J equals 3/2 and J equals 1/2 threshold. And we have a series of Rydberg states converging onto the two of these ion thresholds. So again, we can use the synchrotron radiation to pick out individual levels of these Rydberg manifolds converging on either of the two thresholds, and then use the laser to ionize into the continuum and extract out the beta parameters. in this case, the spin-orbit coupling is first coupled in the core, so we get a different coupling scheme. We use the JK coupling scheme, and this is related to the notation you can see here. Okay, so the first approach that we thought we would take here is to make the approximation that the spin-orbit coupling in the continuum has no effect on the matrix elements. And this essentially reduces the problem to having excitation to the D intermediate state and ionization either into a P or an F wave. And again, the phase difference between the two outgoing waves. So again, we've in some way reduced the problem to only 2 parameters. Now, this works reasonably well for the core of total angular momentum 1 halves, but for the 3 halves case, it breaks down because it predicts that we should have a beta parameter of 0, whereas we actually measure a beta parameter of 0.35. So essentially, the moral of the tale is that you can't make this assumption that the spin-orbit coupling in the continuum does not affect the results. So you really have to take into account all of the open channels. And for the 1 halves case, there's 3 open channels, whereas for the 3 halves case, there's 5 open channels. And you need to take into account all of these. And again, these are calculations on quantum defect calculations done by Andrei Mikhailich, in which he managed to reproduce the results, including all of these channels. Okay, so the last example I want to give from the synchrotron plus laser work is going to be based on xenon. And in this case, I'm going to talk about the effect of nuclear spin on the photoelectron angular distribution. Now, already in 1973, Serge Roche, when he was at Stanford, observed the effect of the coupling between the nuclear spin and the total electronic angular momentum in cesium, and saw how that changed the time-dependent alignment of an excited state. So what they did is they excited in cesium with a laser source. They coherently excited a number of hyperfine split states, and then looked at the fluorescence from these states and saw that there was a quantum beat on these due to the precession of the total electronic angular momentum around the new total electronic, the new total angular momentum due to coupling to the nuclear spin. Later, this was also observed in photoionization from the group of Berry and co-workers. But I guess the novelty in the experiments that we've done is that we've picked an atom, xenon, which has a mixture of both spin 0 and non-spin 0 atoms, indeed, or natural isotopes. Indeed, the 3 halves and 1 halves have approximately a 45% abundance, whereas the spin 0 atoms are about the rest, essentially 55%. So we can use the coincidence method I talked about earlier to be able to look at photoelectron angular distributions from spin 0 and non-spin 0 atoms. So the excitation process, which we chose for this, and I should mention that these experiments were done at the ZIR beamline at Soleil. The excitation process that we chose for this is to excite from xenon with the synchrotron radiation, the 5p atom orbital into a 5d state, and then with a second optical laser to go via a second resonance, so this is a double resonance experiment, into a 4f prime state, which converges on the second ionization threshold. This state then undergoes autoionization to the ground state of the ion and emits an electron. And we will go and look at the angular distribution of this electron, essentially. Okay, so if we concentrate on the lower half of the slide, what we can see is that we can now use the coincidence method to pick out the ions which have 0 nuclear spin. And we can look at the electron velocity map image, which is formed in coincidence with these. And you can see that the image is essentially quite quadrupolar and has strongly peaked in 4 directions. And this is due to a strongly negative beta 4 parameter. But the interesting point to note is that if we look at the photoelectron image taken in coincidence with the I equals 1/2 atoms, you can see that the angular distribution is much more isotropic. And this is, in fact, it's due to the coupling of the nuclear spin in the intermediate state, which leads to a depolarization of the intermediate state and leads to a blurring of the photoelectron angular distribution. Okay, so, well, in a series of papers, we've gone and investigated this in detail thanks to calculations by Elena Gryzlova and Alexei Gryzmailo. in which they were able to show that we really need to include all of the, like the case of neon, we need to include all of the channels in the photoionization process to be able to describe well the ionization dynamics, the beta parameters which we have measured. So on the left-hand side here, you can see the case of the beta parameters as we vary across the Fano profile of the two-photon resonance compared to theory, which is the solid line. So then once we had used the spin zero case to establish well the atomic photoionization model, we could then go back and look at the more blurred images due to the coupling with the nuclear spin and extract information on the hyperfine coupling in the intermediate state. So in some ways, we've used photoelectron spectroscopy to look at the hyperfine splitting in these atoms. Okay, so that's the end of the first part of the talk. And now I would like to change topics and go to a completely different experiment. So it's no longer atomic physics. This is excitation of helium Rydberg's atoms inside in helium nanodroplets and looking at how these relax in time. And this experiment was done at the Fermi free electron laser in Trieste in Italy. Okay, fortunately for me, on Friday, Professor Paul Shire gave a very nice talk about the properties of helium nanodroplets in general, so I don't need to go into that much detail. I could just make a very quick summary that the helium nanodroplets are extremely cold, obviously. They've got a temperature of about 370 millikelvin. They've got characteristics of superfluidity, and they interact very weakly with IR and visible radiation. This means that they are ideal cryostats for doing spectroscopy of molecules in the microwave or IR region. But the point which is more important, at least from my point of view, from the free electron laser point of view, is that they interact very strongly with VUV radiation. So this is fluorescence excitation spectrum taken from the work of Thomas Muller. And on the top of the slide, you see the excitation spectrum for very small droplets, so 80 units. And basically what you see is something very similar to the atomic spectrum, where you've got in narrow lines due to the 2p, 3p, 4p, et cetera, excitations. On the other hand, in slightly bigger droplets here, we're talking about 2,000 atoms almost, what you get is the development of these broad bands, which are shifted to higher energy with respect to the atomic transitions. And this is due to excitation, let's say, of the confined Rydberg state inside the droplet, which essentially shifts the energy of the excitation to higher energies and broadens it out. And this is the kind of excitation that we're going to be looking at. Okay, so the experiment was done, as I said, at the low-density matter beamline at Fermi using a helium nanodroplet source developed by the group of Frank Stinkemeyer of the University of Freiburg. And as described by Paul Shire, this works by evaporative cooling. We can just simply change the temperature of the nozzle and change the average size of the droplets formed. So we can form droplets in the range from a couple of thousand to a couple of 100,000 units, essentially. So the experiment involves exciting with the free electron laser into this 2p band, let's say, to excite a 2p Rydberg state confined in the droplet, and then come along with a UV laser and ionize that into the continuum. And then delay this UV laser in time and see how this dynamics evolve in time. Okay, so this is one example that is for excitation with 21.5 eV, so on top of that 2p band, and ionization with the UV pulse 500 femtoseconds later. So what you see in the top, in this velocity map image here is this very weak line. Here it corresponds to electrons of about 16 eV, and they're actually due to just a multiphoton process from the free electron laser, where you excite at least 2p atoms, orbitals inside the droplet. They come together. One atom goes back down to the ground state, and the other kicks out an electron. And this is some kind of ICD penning kind of process, which we've already heard about in this conference, and we've also studied this extensively both at the synchrotron and at the free electron laser. But for this talk, I'm more interested in the slow electrons, the very low energy electrons which result from photoionization using the UV laser. And these produce electrons in the range from 0 to 2 electron volts. So what does this look like if we plot the photoelectron spectrum, which is on the y-axis, as a function of the pump probe delay? Essentially, what it looks like is that we get, at 0 time, we get the formation of electrons somewhere in the region of about 1.7 eV, which we think corresponds to the confined 2p state. This then relaxes on a time scale of about 3 to 400 femtoseconds before finally seems to be a jump in the photoelectron energy down to emission of a 2s state. Now, this is the energy here corresponds to ionization of a singlet s state, so it's a 1s, 2s state. So it would seem that essentially what we think we have is formation of a metastable bubble, which then grows in time, moves towards the surface of the droplet. The droplet then collapses, and we get the formation of a weakly bound 2s state on the surface of the droplet, or indeed even emitted into the continuum. So this is why we get this 2s peak. Okay, so this is an extremely difficult process to model. As you can see, there's like 20,000 atoms. So from an ab initio point of view, it's very difficult to model, although we have some collaborators who are working on this at the moment. But in the meantime, we've decided to develop a very simple model to trying to give us an idea of at least the basis of the dynamics going on. So we've used a couple of different ingredients. We use a size distribution where in the bulk of the helium droplets, where we see that the average distance between helium atoms is about 3 angstroms. We then take the pair potential for the 2p and 1s2p and 1s2 atoms, and you see that there's a repulsive part of the potential in the long distance range. We then say that, okay, let's say we've got a coordination number of 6, so we've got on average 6 helium atoms around the excited state. Then we can say that we can simply multiply this pair potential by 6. And then if we transfer or project this size distribution onto this repulsive part of the potential, we get something that looks vaguely like the absorption cross-section. So it's an extremely basic model, but we'll see now if it gives us the time scales that we observe in the experiment. So the idea is that we can now run a very simple classical trajectory from this point and see how long it takes for this, let's say, bubble to grow. And just plotting the size of the bubble as a function of time due to this classical trajectory, we see that after 400 femtoseconds, the bubble has grown to about 6.5 angstroms. And that corresponds reasonably well with the bubble size calculated for the triplet state, and corresponds reasonably well to what we've seen in the experiment. The other point is that we can look at how far this pair potential has then gone from the rather flat ionization potential, and we see that the photoelectron should lose about 200 milli-electron volts in the same time, which is pretty much, again, in fair agreement with what we see in the experiment. So as a very tentative interpretation of the dynamics, what we think is happening is that we get a very fast localization of the 2p excitation on faster than the time scale of our cross-correlation function. We then get bubble expansion and relaxation into a 2s state on the surface of the droplet, which is very slowly released from the droplet. And you can see on the long time scales, you can still see this signal growing. Okay, so that's pretty much it from the experimental point of view. I wanted to finish by thanking all of the people who are involved in these experiments, and these are extremely large experiments, and as you can see, there are large groups involved. I would like just to pick out a couple of people. There's Lorenzo Valdi, who's the team leader of our group in Rome, and we were the driving force, let's say, at the experiments at gas phase. Michael Mayer, who is from the European XFEL, who is the PI and proposer of the experiments on xenon at the Desir beamline in Soleil. And finally, Marcel Mudrich and the group from the University of Freiburg, who Marcel is the proposer of the beam time on the helium nanodroplets at Fermi. And with that, I'd like to thank you for your attention.